So far we have talked about the controller, and the controller's job is to control. To control means to maintain something. What can be maintained is only a DC entity. VD and VQ are DC. That is the greatest advantage of VD and VQ. So based on all my computation, I say I want VD to be 20, I want VQ to be 10, something, and the PI loop can execute the error computation cycles and ensure that those levels are maintained. But what is actually getting applied to the motor is not the DC values, but AC. So let us look at how the AC world plays out, and that is what is going to be happening in the real world. And in the interactions between the motor and the controller, we will constantly be switching from the AC to the DC and again back from DC to AC. Okay. We will keep doing this exchange, because we can do control only in DC, but the motor will run only in AC. So let us quickly recap about AC, alternating currents. When I say alternating current, it can be alternating voltage, anything that is sinusoidal. So any sinusoidal waveform is characterized by what is called the amplitude, and that is the peak value, a frequency and phase. Frequency can also be represented as angular frequency by multiplying it by 2 pi. So an easy way to visualize it is that if I have a oscillator, a simple harmonic oscillator, which means a mass tied to a spring which is bobbing up and down, then if I plot its height versus time, its position versus time, that will be a sine wave. Another way of visualizing a sinusoidal waveform is that if I have something that is going with a uniform angular speed in a circle, then the shadow that it casts, the length of that shadow with respect to time is a sine wave. Fine. And I can also represent the sine wave using a cosine equation. That is why I have written it there as cos omega t, but cos means when t is 0, the amplitude will be maximum, whereas what you are seeing in the picture is that when time is 0, the amplitude is small. So I have to give a phase offset. I can put phi is equal to negative 90 degrees and it will describe this equation. Fine. Now let us look at what is called a 3-phase circuit. We will be looking at what is called a star connected, because that is what we use in the motors. Before which I will tell you that there is a, when there is a sinusoidal waveform, it is going up and down, it does not have a constant magnitude, magnitude is rising, falling, then rising in the negative side, coming back to 0. So it is not having a magnitude which is constant. So as a measure of how big the wave is, if I ask you what is the average magnitude, you will say it is 0, because it is equally plus and minus. So in order to get rid of this, and if you say the average value is 0, it does not give me any information, it does not give me a sense of how big the wave is. So in order to get rid of this absurdity, what I will do is I will simply square the wave. So if the height is 1, when I square it, it becomes 1, and if the height is negative 1, when I square it, it also becomes 1, and then if I add, I get 2, that is a measure of how big it is. If the wave was to begin with 2 in the plus direction and minus 2 in the negative direction, when I square it, I will get 4, and I will get for the negative part also 4, and if I add, I get 8. So in the first case, when the amplitude was 1, when I squared and added, I got the answer as 2. In the second case, when the amplitude was 2, when I squared and added, I got 4 plus 4, 8, but then it gives me the wrong impression that the second wave is 4 times bigger than the first, which is wrong. and I get that impression because I squared it. So, to compensate I will take the square root again. So, for the first wave I will say its magnitude is not 2, but root 2, and for the second wave I will say the magnitude is not 8, but root of 8, which is 2 root 2. Then if I compare root 2 with 2 root 2, I know that the second wave is 2 times bigger. So, this way of squaring, adding and then finding the square root is called RMS, root mean square. Now, if I want to measure current, what I will do is I will place an ammeter over here. When the voltage is sinusoidal, the ammeter is not going to be rapidly moving up and down, because the frequency with which it is going up and down is very fast. The ammeter will be calibrated in such a way that it can show me some average value, and as we discussed, there is nothing called average with sinusoidal. What we mean by average is the RMS value. So, the ammeter will show me the RMS value of the current that is flowing. If I place another ammeter here, that will show me the average, meaning the RMS value of the current that is flowing in the other phase. There are 3 phases. The 3 phases are the same, except that they all have a phase difference of 120 degrees, 120 degrees or 2 pi by 3. But when I place an ammeter which is only showing me the RMS value, I will actually measure the same current in all the 3. The line current and the phase current are the same. Line means what is flowing like this, and phase is just what is flowing from here to here. From here to here is the phase, and what is from one end to the other is the line. The currents are the same, but when I look at voltage, this is V A, let me say, and this is V B. If V A is V cos omega t, V B is V cos omega t minus 120 degrees, and the total voltage is V A minus V B, line voltage. So, V A minus V B, V A is some voltage that we know, the RMS value is V, but the V A minus V B, which is the line voltage, is V cos omega t minus V cos omega t minus 120 degrees, which is 2 pi by 3 radians. If you expand this trigonometrically, you will get that the line voltage is root 3 times the phase voltage. If it were not an AC current, you will think that no, it will be double, because there are 2 of them in series, but the 2 of them are in series, but they are not of equal magnitude. When one is high, the other is small, when the other is small, this one is high. So, on the average, if you see, it is only root 3 times more, it is not 2 times more, fine. Now, let us look at the currents a little more carefully. The 3 phases are commonly represented as U, V and W. They can also be described as A, B and C, small a, small b, small c, these are all different conventions. So, if the U phase current is represented by omega t, then the V and W are 120 and 240 degrees apart. The interesting thing is, if you add all of these, you can of course expand them trigonometrically and add them, but without doing all of that, you can just look at Kirchhoff's law and say that the total current should be 0, and you will get the value to be 0 when you expand it. But if you expand them as vectors, what are called phasors, then you get a different kind of expression, and when you add them, you get 1.5 into I into cos omega t, which is essentially 1.5 times bigger than this, and it is a rotating vector, it is a rotating current. We will see this graphically going forward. Before getting into that, we know that the electric vehicle is powered by a battery and the battery gives only DC, but the motor needs AC. So, we will take a small detour and see how we convert DC into AC. Just imagine that I have a battery and I have connected it to some load, some resistance, and I am putting a voltmeter and I am measuring the voltage across the resistance. Let us say the battery is 10 volts. If I switch it on and measure, what will the voltmeter read? There is a resistance and from here to here I am applying 10 volts. So, if I stick a voltmeter, it will read 10 volts. If I the whole thing went okay. If I open the switch and then connect the voltmeter, what will it read? What will the voltmeter reading be? I have opened the switch, it will show no voltage, 0. There is no voltage across the resistance. My voltmeter is from one end of the resistance to the other end of the resistance. Okay. So, my voltmeter will read 0 when the switch is open. If I close it, it will read 10 volts. But imagine I have a certain superhuman ability, I can turn on and turn off the switch 10,000 times every second. And what I do is, what I have done is I have sliced 1 second into 10,000 intervals. In each interval, I have the ability to flip the switch if I want. Understand? And what I do is, I flip by waiting for 3 slices of time, I keep it on. Each slice is 1 by 10,000th of a second. For 3 slices of time, I keep it on, and then for the next 7 slices of time, I keep it off, and I keep repeating it till the 10,000 slices of time are over. And during that entire 1 second, I have connected the voltmeter, I am trying to see what its reading is. What will it read? It will read 3 volts, because on the average 30% of the time 10 volts was on. Fine. In the next second, if I choose to keep it on for 4 slices of time and then off for 6 slices of time and repeat it for 10,000 slices, then the voltmeter will read 4 volts, because 40% of the time I kept it on, 60% of the time I kept it off. So, this percentage of on off time is called the duty cycle. 40% duty cycle means 40% of the time it is on. By doing this, I can get whatever voltage I want from the battery, provided I do not want any voltage more than 10 volts. The maximum voltage I can get from the battery is only 10 volts, but anything less than 10 volts, if I want 6 volts, 6 by 10 is 60%, I will just keep my switch on 60% of the time. If I want 8 volts, I will keep my switch on 80% of the time. I can get any voltage I want from 0 to 10 volts by changing the on off time. So, if I want a sine wave like the green wave that you are seeing in the picture, at different instants of time I want different voltages, and at all of those respective times I will change the percentage of on off time. This is called pulse width modulation. Fine. The sine wave may be something like 50 hertz or 100 hertz, but my on off is happening at 10,000 hertz, much higher frequency. So, whatever you are seeing here as, let us say 1/10 of a wave is actually a few thousand cycles in my switching on off. Fine. And you see here that the widest pulse is this. This width tells me what this height is. If I were to make all the pulses proportionately wider, I can get a wave of large amplitude. And how quickly I run through this cycle and then come back again for the next cycle is also another thing in my control. By this I can change the frequency of the sine wave. So, the percentage of on off, the sequence in which I vary, what is the maximum to which I go before I start coming down, defines the amplitude of the voltage, and how rapidly I go through that cycle defines the frequency. And all of this is under my control just by having a switch which I can rapidly turn on and off. Fine. So, this is how I convert AC into DC, and you see that if I have a AC source, if I have a DC source like a battery, I can get a line where I get a AC current of my choice, as long as the peak is not more than the capacity of the battery. That is another important point I want you to note here. I cannot get a wave which is like this, because the battery will simply not give. Even if I keep it on 100% of the time, I will only get up to here. So, what will happen if I try to do that is it will go up to there and then it will flatten and then come. Okay. So, on this note I will also come back to the point that we earlier discussed about 34 volts. I said 34 volts is the limit of the battery. Actually, the battery can give 48 volts. If the battery can give up to 48 volts, I can draw from it any voltage less than that through pulse width modulation, but the maximum voltage I can get from the battery is how much? 48, and that 48 is this peak. If the peak is 48, what is the RMS? What is the VRMS? It will be root 2 times 48, and that is 34, 33.9 something. I am sorry, by I keep making that mistake. 48 by root 2, 48 into 0.707. Okay. So, this is where we get that funny number called 34, because the battery is 48. Now, what we want is not just AC, we are greedier now. We want to get 3 phase AC. How can we get 3 phase AC from DC? Are we past time? Okay. So, this topic is actually very fascinating, but I will not go too much in detail into it, because I only want to tell you as much as you need to control the motor. I do not want to overload you with information. essentially a set of 6 switches is all that I need to convert a DC power source into a 3 phase AC. We have actually 3 switches on the top, that is called the high side, and 3 switches at the bottom, which is called the low side. The very important thing to remember is do not close 2 switches at the same time in one line, because then what will happen? You are short circuiting the battery, you will have nothing short of an explosion. The entire battery will discharge in a fraction of a moment, and you will have catastrophe. So, normally in the hardware that you buy, it comes as a built in standard feature that even if you try, you cannot close 2 of them at the same time. It is a built in protection feature, but short of that you can do anything. And what is normally done is, if the high side switch is closed, we call it a 1. By default, the lower switch will be open. I have no choice about it. And if the upper switch is open, the lower switch gets closed. I have no choice about it. So, this minus is the complement of the plus. Whatever state the plus is in, the opposite state the minus will be. So, from a logical point of view, I do not have 6 switches, I have only 3 switches, because defining any one of those 3 switches defines the other. But each of the 3 switches can be in one of 2 states, either 0 or 1. So, what are the total number of states possible? This can be in 2 states, this switch can be in 2 states, this can be in 2 states, this can be in 2 states. So, what is the total number of states? It is 2 into 2 into 2, 2 to the power 3, 8, out of which, so I can number them serially as 0, 1, 2, 3 up to 7 in the binary form. 0 to 7 there are 8 states that the system can take, and out of that, if I keep all the 3 open, that is the 0 0 0 state, and the last state is when I keep all the 3 closed, 1 1 1. In both these cases you will find that VAB, VBC and VCA are 0. It is as if I am not applying any voltage. The remaining 6 states, VAB, VBC and VCA, will be either 0 or positive or negative, and changing from one state to the next involves changing only one bit binary, which means any one switch flipping is the sequence. So, there is a lot of charm in the way the whole thing has been designed, it is very beautiful. Let me erase all of this. This is called a hex bridge, by the way. What is written there on the left? Because there are 6 switches. And what happens is that by switching them in sequence, the resultant vector which I told you, IU plus IV plus IW, is shown in black. It is 1.5 times in length, whereas the 3 faces, the U face is red, it is oscillating, and the other 2 faces are green and blue, they are oscillating on different phase. And how the sine wave looks is shown on the right hand side, and the sum of them is 1.5 times bigger, and it is also travelling, which means it is a rotating vector. So, it is very charming. You can spend an entire day just trying to understand, it is almost lyrical and poetic how this thing works. I will recommend that you visit this website called switchcraft.org. It is a beautiful website created by two young engineers from Norway, and with a lot of detailed and well illustrated animations and diagrams. They explain how the whole thing works, but I will not get into all the detail now. Before signing off, here is an assignment for you. A motor is powered by a 48-volt battery. What is the maximum phase voltage and what is the maximum line voltage which can be applied, RMS. The motor is of 6-pole construction and I know the back EMF constant, it is 8 volts per 1000 RPM. What is the maximum no load speed at which it can run if I do not do flux weakening? We already know that if I do flux weakening, I can make it go at much faster speeds, but if I do not do that, what is the maximum no load speed at which I can run it? And if I run it at that speed, what will be the frequency of the voltage? They are not complicated in terms of calculation, but they will require you to apply a number of concepts that we have learnt at different stages in the previous lectures.